So the experiment we are going to see today, it is steady state error constants for three different types of systems, type 0, type 1 and type 2. Now what is this particular steady state error is? It is a measure of system's accuracy. Right? It is a measure of system accuracy. What does this mean is, if you have these constants value equal to 0, it means that your system is a stable system. If you have some kind of a constant value for the steady state, then it means that your system is slightly an unstable system, which always has some kind of an error. So before we proceed, right, how do you find the steady state error constant is, you have a system, I am just roughly giving you have some kind of a system, you will be giving some input here and you will be finding the response, right. So this input, either it may be a step input or it may be a ramp input, right. So it can be any kind of inputs that you have, and the output that you see, it is the response that you are going to measure, and this response is what is important to us. This response, either this may be a time domain response or it may be a frequency domain response. We are going to handle this time domain response, okay, and this time domain response we will calculate by using the transfer functions. Now let me give you a larger picture of what kind of response or what kind of systems that you will be having. This response also, when you are using a time domain response, either it can be a steady state response, right? Either it can be a steady state response or it can be a transient response. So these are the two different kinds of responses. Now what is the steady state response is, if you consider the complete response here, right? For a given set of input, this is your time scale, this is your amplitude. So once there is a change in your system, what happens is your response will start oscillating, right? And then it will go to a steady state value. This region is what is called as a steady state we measure, and this particular region of response we call it as a transient response. Okay, any system will have both transient system and steady state system, but it may not be 100% required that you always get a steady state response. Okay. Now before that, let us take a generalized transfer function diagram or a band diagram, block diagram for the type. So you have a summer here. This is fed to the transfer function system G of S. This may be either type 0, this may be either type 0 or type 1 or type 2 systems, and then you will have your output Y of S. And from output Y of S, we feed it back to our input, and this we can consider it as the error that we are feeding, right? So E of S is nothing but your error, and input, let us consider this to be some R of S, right? So R of S, either it can be a step input or it can be a ramp input or it can be a triangular input or whatever the inputs that we have. Now this and this we are going to subtract. So what is E of S here? E of S is here is nothing but R of S minus Y of S, right, from the output system. And what is Y of S? Y of S is nothing but G of S multiplied by E of S. G of S multiplied by E of S. Now substituting this Y of S over here, it is E of S will be equal to R of S minus G of S dot E of S. Okay. So we will rearrange this expression. So E of S, when you take it common and bring this on the other side, you will have 1 plus G of S equal to R of S. And what is this E of S is? E of S is nothing but R of S upon 1 plus G of S. Now when you take the inverse Laplace transform of EFS is what you will get the error values. Okay. Now, please remember, recall what is this EFS? EFS is nothing but the steady state error in Laplace domain. RFS is nothing but your input response or input function. GFS is nothing but the system that you have. Either this may be type 0, type 1 and type 2. Now recall the title. What is our objective here? Our objective is to find a steady state error constant, this particular value EFS, for type 0, type 1 and type 2 system. In the experimental setup that we have two different kinds of inputs. We have a step input and we have a ramp input. Now I hope the picture is clear. Our objective is to find out this EFS for two kinds of inputs and for three different kinds of systems. Okay. Now before we proceed, let me give you, okay. First let us consider step input. Okay. How do you define a step input? Step input is, right, where this is the amplitude part and this is the time domain. How do you represent it? Your R of t is equal to A in this particular period of time, right? So let us assume that this is equal to 0 to t1. So between 0 less than t less than t1 and 0 t1 greater than or t greater than t1. Okay. So t greater than t1. And in Laplace domain, how do you represent? You will represent this R of s as A upon s. Right? A is nothing but this amplitude height. Okay. Now you have to feed this R of s equal to A upon s in this particular system. We are giving a step input. And what is a type 0 system? Type 0 system also you have the transfer function of a type 0 system. Now when you substitute a type 0 step input system, I will directly give you the steady state expression. We represent the steady state expression in an inverse in time domain response as A upon 1 plus Kp, right, where Kp corresponds to the type 0 system. This is for a type 0 system and an input of step input. Okay. Similarly, your ESS will be 0 for a type 1 system and similarly your ESS will be 0 for a type 2 system. What does this mean? It means that when you have a type 0 system, you will be having some kind of a steady state value. Steady state error will always be there. Whereas in case of type 1 and type 2 system, there will be no error. This is a steady state response and not a transient response. What does this mean is, say for example, I am giving a step input here. I am giving a step input, right? So this is the amplitude part. I am going to represent this magnitude as A. When you are using a type 0 system, you will be having some kind of an error. It means that the response, so this is actually your input. Now the output response will be is, you will always have some kind of an error like this in the magnitude part. Right? You will always have some kind of an error. Okay. And this particular value is called as the error or the error constant ESS value, which is equivalent to A, that is amplitude, upon 1 plus Kp, the constant factor for the type 0 system. Now this is for type 0. Now what will happen for type 1 system? Type 1, your error will be 0, right? So, and this is a steady state error. How the response will be is, the response will be something like this and then it will have a steady state value. You will have some transient response and then you will have a steady state value. Right? So this is how this oscillations is what you will have for a type 1 system. In case of type 1 system, type 2 system, it is a parabolic response, right? So it is a second order system that you have. So this oscillations also you will not have. So maybe I will draw it in a separate way. This is the input that you have. In case of a type 2 system, your oscillations will be very flat, right? So you cannot in fact see better. It will be very small, and you will not have even such a kind of a response, right? So this is what we are going to see experimentally also. So we will go back to the table, and then we will start our experiment. Okay. So this is the experimental setup that we have here. What is that we have is we have a power on button, and this is the input sections. You can give either a square input or you can give a ramp input from this, and you can have amplitude adjustment, frequency adjustment, and off time adjustments and amplitude adjustments for this ramp setting. Now, and these are the system that we have. This is a type 0 system, type 1 system, and type 2 system. Type 0 system, it is just the proportionality constant K. Type 1 system, the proportionality constant is 1 upon T1S, which is the G of S. And for G2 of S, it is 1 upon T2 S2. Okay. Now, first let us give a step input, and then we will give a ramp input, and then we will see how the response is going to be. So, the first thing that you do is you connect your input, right? Let us connect the ground here, the square term, square negative of this, and then we have to monitor our inputs, right? So what we will do is we will first give the input from the oscilloscopes, right? So this is our input from the oscilloscope, and then the negative terminal we are giving it to the negative of the probe. And then the positive reference voltage we will give it to the positive. Okay. And we have to connect this EFS to either K1 or K2, right? So we can give to any proportionality constant. It is just a change in the proportionality value. So we can give it to K1 or K2 also, it doesn't matter. We have to see our response now. So we will see our response across Y of S. Okay. Now you look at the monitor here. What you see here is the yellow one is what is your input is, and the green one is what is your output responses. And you see this particular difference, that there is a error here, and this value corresponds to A upon 1 plus Kp. Now let us change the setup to a type 1 system. We are giving the same square input only. All I need to do is remove this particular part and give it to my type 1 system. When I give it to my type 1 system, my response, again we have to look here. Now look at the response here, right? This is one part of the square wave in fact, right? So your square wave in fact it starts here as the input. So you see here that there is a steady state time it is taking place, and after some period of time they in fact settle down. Okay. So they in fact settle down to a constant steady state value, right? So this is how the response for a type 1 system is. Now let us change it to a type 2 system. Okay. And now let us look at the response again, right? So yeah. Now look at the type 2 system's response, right? You are having a lot of transient responses here, and then it is reaching a steady state value, right? If you increase the frequency value, if you increase the frequency, I mean that is the maximum that we have here, you will reach a steady state value. Okay, so this corresponds to 0 values of your steady state. Now let us repeat the same thing with the ramp setup. So all I am doing is I am changing it to a ramp input here, and you see in this ramp input, Yeah. You see in this ramp input, right? Initially you are having some kind of a transient analysis, and then they are reaching a steady state value towards the end. And when there is a transition again, you have this transient response, and then they reaches the steady state value. Now let us again go to a type 1 system. So this is the type 1 system, right? So there is a very small error, but still they are reaching the steady state value, so right? So you see here that there is a slight difference, but still they reach your steady state value. For a given input of step input, now look at the response, you will have a steady state error value. Yeah. Yeah. Okay. Now look at this, your yellow is your input and the green is your output, and you can see lot of error that is taking place, and that is because of the type 0 system.